All right, shall we get started? Okay, so hi everyone. Sorry I'm not there in person, but we are very happy to have Ivanna Escala as our colloquium speaker this morning. So as you all know, Ivanna has spent the last 2 years at the Observatories as a Carnegie Princeton Fellow. Prior to that, she earned her PhD in 2020 from Caltech, working with Evan Kirby. Ivanna is one of the world's experts on the chemical abundances and stellar populations of M31. And she's continued working on that during her time here, as well as expanding her research to cover the rest of the local group as well. Ivanna's finishing up the first half of her fellowship in the next couple months, and then she'll be moving to Princeton for the second half of the fellowship. And so we're looking forward to continuing to see her, collaborate with her for the next several years. And so with that, let me just make sure everybody is muted. For those of you online, if you have questions, you can enter them into the chat, and hopefully Shannon can read those out. And so Ivanna, take it away.
Thanks for the introduction, Josh. And let me know at any point if people on Zoom, if you're having any difficulty hearing me, and I can speak louder. All right, so I'm happy to be here today to give my goodbye colloquium. The last less than 2 years have gone by really fast. I started at Carnegie in August 2020. So I'm happy to take this opportunity to really highlight the work that I've done since arriving here. So as Josh stated, I have done a lot of work in disk galaxies, particularly in M31, but I've also been expanding to some isolated dwarf galaxies in the local volume. And my focus is really to use chemodynamics as a probe of galaxy formation in the local group. Okay, let me make sure this goes. There we go. All right, so first off, why study nearby galaxies? So local galaxies provide detailed views into the distant past in a way that is highly complementary to high redshift studies of galaxy formation. So here I'm showing a simple schematic of the history of the universe, beginning with the Big Bang and going up until present day, to the galaxies that we see around us in the local universe, including galaxies like M33. So as a consequence of their proximity, we can study these galaxies in exquisite detail. We can resolve individual stars with great photometric precision, and also we can investigate individual stars spectroscopically within the local group. So this is something that's currently not possible beyond the local group and going into the local volume. As a consequence of the fact that stars within these galaxies are extremely long-lived, for example, red giant stars will persist for billions of years, we can use this precise photometry and this resolved stellar spectroscopy to reconstruct the accretion histories and just the general formation histories of these galaxies in the local universe. So another reason that studying galaxies in the local universe is fairly ideal is that we can study both larger scales of galaxy formation that correspond to Milky Way-like galaxies, such as M31, but we can also study the smallest scales of galaxy formation. So these are dwarf galaxies and going down to ultrafaints. So just as an illustration here, I have a simulation of the formation of the local universe. It's centered on a Milky Way M31 mass pair. This is from the CLUES simulations, and it's a 10 megaparsec volume. So on both the scales of dwarf galaxies and Milky Way-like galaxies, we do expect that they will form hierarchically, right? So this is a much more significant or dominant process for the Milky Way-like galaxies. And dwarf galaxies will experience mergers at early times, but even at late times within these types of volumes, we do expect to see evidence of some dwarf galaxies that have experienced recent interactions with other dwarfs. So the local volume is truly the only environment in which we can test the hierarchical assembly paradigm in detail, given that we can access these faintest systems in terms of galaxy formation. So what are some outstanding questions for the hierarchical assembly of disk galaxies? This may be a biased list of questions in the sense of what I'm interested in specifically, So first off, an outstanding question is, what is the mass function of destroyed galaxies? So here I'm showing a very famous image from SDSS. This was made by Ivanna here at Carnegie and collaborators, looking at the field of streams in the northern sky, including the Sagittarius stream here. So there are just questions regarding what are the properties of the progenitors that form the stellar halo of the Milky Way. For example, what is their mass distribution? What are their metallicities? So in general, most of our existing constraints do come from the Milky Way. So it's particularly important to expand to other galaxies in the local volume to see whether what we know from the Milky Way is broadly applicable. A related question is, what is the in situ versus accreted halo fraction for Milky Way mass galaxies? So the accreted component is made from these destroyed galaxies, but the in situ halo fraction can also be intrinsically related to the merger history of the galaxy. So this relates to the question of what are the formation channels for the in situ halo. So we know from the Milky Way that we see evidence for a population of kicked up disk stars in the stellar halo, and that otherwise it seems to be highly dominated by external galaxies that were accreted. But we don't have this level of constraints, again, for other systems quite yet. And lastly, a question that's particularly important for M31, as I'll explain later in this talk, is how do disks survive significant late time mergers? Also, how common are these? And what are signatures that a galaxy has experienced this, within the last few billion years? Okay. So this talk will be separated into two parts, the first of which will focus on my work on the Andromeda galaxy. This is still, a large part of my research portfolio. So I'll start by emphasizing this before going on to my ongoing work with isolated dwarf galaxies in the local group. So in my opinion, M31 is ideal for studies of galaxy formation beyond the Milky Way. So it's the only Milky Way-like galaxy that we can currently hope to study in a level of detail approaching what is even, that is comparable to what we have achieved in the Milky Way. So in this sense, it can be used as a complementary template, but I also think that it's, of course, an interesting galaxy in its own right that is worthy of being understood. So to further motivate studies of M31, I like to show this image that shows the moon to scale, where the moon is approximately a half a degree in diameter on the sky. So you can see that even the visible portion of M31's disk is a few times the size of the moon on the sky. And if I embed it within a star count map from the Pan-Andromeda Archaeological Survey, the true extent of this galaxy on the sky, as well as its structural complexity, becomes apparent. So we can see all three stages of the minor merging process represented within this image. So we have intact satellite galaxies like M33 that are in the process of infalling and will ultimately be disrupted in the far future. We have the fairly smooth component of the stellar halo, in which we currently cannot photometrically or kinematically detect substructure. This extends out to at least 175 kiloparsecs from the center of M31. We have stellar streams that result from the ongoing disruption of galaxies, most notably the giant stellar stream, which spans at least 6 degrees or so on the sky. And we also have the disk of M31, which, as I was just emphasizing, does not evolve in isolation from the halo, particularly in the event of high mass ratio merger events. So what do we know so far about M31's merger history from previous photometric and spectroscopic studies? So first and foremost, we know that M31's merger history involves the recent accretion of a relatively massive galaxy. So this accretion event is thought to have occurred within the last 4 billion years. So evidence in favor of this scenario comes from things such as a global burst of star formation that occurred 2 to 4 gig years ago across the entire surveyed region of the northeastern disk. This type of information comes from the panchromatic Hubble Andromeda treasury, which I'm showing here, along with a map of some spectroscopic coverage of M31's northeastern disk. M31 also has a much steeper age velocity dispersion relationship than the Milky Way. It's about a factor of 3 times higher for the oldest stellar types. And it also has significant asymmetric drift, so lag between the rotation of its gas disk and its stellar populations. That is also age dependent. So these two last things are indications that it's experienced significant heating over the course of its evolution. We also see evidence for slowly rotating inner halo along the major axis, and also some indirect evidence for a population of stars with halo-like kinematics, but disk-like luminosity function. So the central question here is, could a minor merger produce these types of observed features in addition to the observed tidal structures around the halo? And here I'm referring to the main tidal features that are thought to be associated, or was this a major merger that occurred within the last few Keck years with something that was the third most massive member of the local group versus something that was more like LMC or M33 mass? So one way that I've aimed to address this question is by studying tidal features around M31 with resolved stellar spectroscopy. So the aim here again is to obtain constraints on the nature of M31's last significant merger. So here I'm showing the footprint of the spectroscopic and photometric landscape of Andromeda's stellar halo, or SPLASH survey. So this survey, which I have been recently involved in, is composed of 20,000 individual red giant branch stars. It spans the halo of M31 as well as the disk and satellite galaxies for over 50 spectroscopic fields. So this is done with the DEIMOS instrument on Keck. So each field spans about 3 kiloparsecs. At the distance of M31, you can target hundreds of stars simultaneously, and they're all roughly 1 hour exposures, which are sufficient to obtain kinematic information and also to perform a dwarf giant separation along the line of sight. So here I'm zooming into the central few degrees of M31 and showing the locations of a number of specific spectroscopic fields targeting the main system of bright tidal features within this galaxy. So that includes the giant stellar stream, which is this overdensity shown here. And there's also a system of diffuse shelf-like features, which may not be the easiest thing to see in this plot, but these dots are the apparent photometric edges of the west shelf and the northeast shelf. Okay. I should also mention that we do have some deeper spectroscopy in the inner regions that correspond to 5 or 6 hour exposures per field. This is from the elemental abundances in M31 survey, which was the focus of my thesis work. Okay, so I'll start with discussing spectroscopic constraints from the giant stellar stream. So from the elemental abundances in M31 survey, we have spectral synthesis-based metallicities within the giant stellar stream. So the first order thing that you can do with this information is get a median metallicity for the GSS and slap it on a stellar mass metallicity relation, such as that that was put together by my thesis advisor, Evan Kirby. So the median metallicity for the GSS is about negative 0.8 dex or so. So if you use an extrapolation of this relation, that corresponds to a stellar mass of about 1 to 5 times 10 to the 9 solar masses. So at face value, this is consistent with something that's more LMC or M33 mass and would correspond to a minor merger scenario. However, it's somewhat more complex than that. So we know that galaxies like the LMC or M33 in the local group have non-inexorable metallicity gradients. We expect that the progenitor of the giant stellar stream would have had the same thing. And we do have indications, right, photometrically, that this indeed is the case. So this should initially be interpreted as a lower limit for the stellar mass, assuming that this may trace more metal pore populations. So the first paper that I published after starting at Carnegie was a pretty systematic study of abundance variations across the giant stellar stream feature. So here I'm just, for the sake of simplicity, showing the relationship between metallicity, again, which is derived from spectral synthesis here, and projected distance from the center of M31. So each of these points are stars and they're color coded according to their probability of belonging to the giant stellar stream. So magenta stars are more likely to be related to the GSS. This is a position and velocity based probability. So what we end up finding is a non-negligible metallicity gradient about negative 0.2 dex per kpc, just in the simple projected radius direction. For some context, that's similar to the magnitude of the gradient in both the disks of the Milky Way and M31. So again, we had previous photometric indications from this, but it's good to have confirmation from this spectroscopically, and also to provide robust constraints for future work modeling this type of event. So presumably this gradient originates, in the progenitor. So one thing we realized after working on this project was that there needs to be more work done on actually connecting metallicity gradients observed in streams and shells on the sky to the properties of their intact progenitors prior to disruption. So this is something that an undergraduate student at UPenn, Jennifer Locke, has been working on. So I am one of her co-mentors, and I mentor her along with Emily Cunningham, her primary mentor, and Robin Sanderson. So Jen's looking at the feedback and realistic environment simulations, particularly the latte suite, and looking at these fairly high mass merger events that involve progenitors with stellar masses greater than 10 to the 9 solar masses or so. So this is a look at one of the simulations she's been investigating, where you see the formation of a giant stellar stream like analog, right, a highly elongated stream, and also a system of tidal shells. So when you look at the associated metallicity distribution functions, you'll notice that the stream actually does probe more metal poor populations, whereas the shell features are more metal rich on average. And the more metal poor stream debris does indeed originate from the outskirts. So what Jen is finding is basically that, yes, the gradient you observe on the sky depends on the gradient in the intact progenitor, but it also depends on the orbit of the progenitor and the way it was disrupted. So hopefully, there will be more work to come out of this in the future, but some initial promising results. All right, so going back to constraints on the nature of M31's last significant merger from spectroscopy. I've been talking about the stream, but what about the system of tidal shells that I've mentioned? So the southeast shelf, which is located here, has been previously been studied. This was actually discovered spectroscopically. It's too faint to see photometrically, at least within the pandas photometry. And the west shelf has also been confirmed to be a tidal shell. But until very recently, the northeast shelf has actually avoided spectroscopic characterization, despite the fact that this feature is, arguably the most important shell for characterizing this merger event. Much of the central debris is predicted to be deposited in this region. So I have a paper that's in the process of being published right now that's presenting really the first large sample of kinematical tracers within the shell feature. There is just previously measurements for a few planetary nebula that were even not clear to be associated with this feature. All right, so I may have spoiled myself a little bit by sort of referring it to a system of tidal shells, but the first thing is we have spectroscopically confirmed that this feature is indeed a tidal shell. And the reason that we know this is this very distinctive wedge shape in this projected phase space diagram. So this is the projected radius from the center of M31 versus the heliocentric velocity that's shifted according to the systemic velocity of M31, which is -300 kilometers per second. So these orange points are just the points targeting that are thought to be red giant branch stars in the northeast shelf, and the gray points here are likely Milky Way contaminants along the line of sight. So shells are formed in merger events that have highly, radial incoming orbits. So owing to the symmetry associated with the event, you can model them analytically, as well as, produce models of them within simulations. So here we're looking at, I guess, the 3D phase space here, where you have 3D radius and 3D radial velocity. And you have an incoming progenitor that's being disrupted, and the shells are formed from successive orbital wraps of the tidal debris. But when you look at this in projection, as we're doing in M31, what you end up getting is basically these triangular shaped wedge features. So again, it's a pretty unique signature. The fact that we see this shape is pretty definitive evidence that this thing is indeed a tidal shell. So we have some information concerning the geometry of the northeast shelf. It's located slightly in front of M31. So we know that the upper envelope here is the returning component of the stream. So it's going back toward M31. So what happens is this is the outgoing stream component in the lower envelope. So you have streams on orbits that are moving away from the galaxy, approaching their apocenter and the systemic velocity of the galaxy and returning toward it. Okay. So we've established that this feature is indeed a tidal shell. It's a separate question whether we can show that it's associated with the giant stellar stream merger event. So in order to assess that claim, what we did is we looked at a couple of comparisons to N-body models for the formation of the giant stellar stream. So these models are fitted to giant stellar stream data only and not data along any of the shell features. Despite that, though, you can see that they're able to qualitatively reproduce the observed shape of the data. So we're looking at the projected phase space diagrams again here, where you have the observational data in black. These are those planetary nebula I alluded to earlier. That was the previous state of the art in terms of kinematical tracers. And we have the satellite debris predicted from the model here in red, and then we have the host model particles here in orange. So this is mostly concentrated at the disk. I should mention here that I'm looking at the predicted, the model over a much larger area than spanned by the data. We actually don't expect this huge disk contribution at the level, at the location of the data. So we looked at a couple of different models, one in which the core of the progenitor remains intact and one in which it completely disrupts. So in addition to the fact that despite the fact that it's not fitted to the shell data, you can see that qualitatively the no intact core model provides a better fit. And this is something that we have also showed statistically, but for simplicity, I think it's easiest to understand just by looking at this plot. The intact core model has a lot more structure that you see within the wedge pattern for the shell. So this was just a preliminary comparison to a couple of N-body models. There's a lot more work that can be done here in terms of comparing to a larger suite of models and also incorporating the shell data as kinematical constraints. All right, so you may be wondering, how does the Northeast Shelf compare to M31's giant streams, the other shelves, and the disk, right? Since we do have this wealth of data from the SPLASH survey that was obtained homogeneously within M31. So we'll look at the projected phase space diagrams again, but build them up slowly for clarity, starting with the Northeast Shelf. So these are those planetary nebula from earlier. This is the giant stellar stream. So what's happening here is you have the tidal debris incoming and forming the stream, and then wrapping back around and forming the shell subsequently. It actually looks as if some of the planetary nebula could be a forward continuation of the giant stellar stream here. So we can actually look at the disk, and you might be wondering, why is it informative to look at the disk? So we didn't find evidence for an intact core at the actual, region of the sky where the Northeast Shelf dominates, but there is some possibility allowed in the N-body models for the core of the progenitor to have been deposited in the disk and embedded there. So if you sort of visually extend the lower envelope of the Northeast Shelf here, we don't see, any immediately clear evidence of this feature, although again, there is this part that could be the forward continuation of the GSS. An extension of the upper envelope would be difficult to detect because this region is dominated by the disk feature. So in terms of the model predictions, we would expect to see a core if it was deposited in the disk, mostly within this velocity range. So we don't detect anything, any feature that clusters in kinematical space or in physical space on the sky. But the SPLASH survey, only extends inward to 4 kiloparsecs. There is some possibility that it could be embedded in the central regions of the disk. All right. So lastly, we'll compare the Northeast Shelf to the other shell features. So here I'm showing it again for just some additional context. The photometric, the apparent edge of the shelf on the sky, it covers a radial range because of the viewing angle. So next, I can add in the West Shelf. You can see that it has a similar triangle shape, but spans a smaller absolute velocity range and also only extends inward to about 25 kpc or so. And lastly, the southeast shelf, which only extends inward to about 18 kpc or so, and has a even smaller, if not comparable, velocity range to the west shelf. So what you're looking at is this sort of concentric system of wedge features. This is pretty clear evidence, in my opinion, for a common origin scenario that's independent of any comparison to n-body models. The simplest explanation, right, for observing these nested wedge features would be that they result from successive orbital wraps of the same progenitor, right, where the orbits are at successively lower energies and closer into the potential or the center of the galaxy. Okay. So we also have some support for a common origin scenario from looking at the metallicity distribution functions of these features. I guess that's like pretty difficult to see on this screen actually, so sorry about that. Trust me when I say that there is an MDF there that is the smooth component of the stellar halo for comparison. Here is the giant stellar stream. And then we can add on each individual shell for comparison. So despite the fact, that these features are located on fairly disparate regions in the sky, we see that the shapes of their MDFs are fairly similar. The west shelf experiences more halo contamination, so that's why you're seeing more metal core stars here. And the mean metallicities of the MDFs are similar. And if you could see the smooth halo MDF a little bit better, you could see that the shell and GSS MDFs are distinct from the background halo population that has been cleaned of substructure. And this is the halo along the minor axis, I should mention. Okay. So in summary, what have we learned from chemodynamics and M31's tidal features? So we know that the GSS progenitor probably had a significant metallicity gradient and was at least as massive as the LMC. So we find that the northeast shelf projected phase space distribution broadly agrees with predictions of GSS merger models that were fitted to the GSS and not the shells. And this is for a minor merger scenario specifically. This type of modeling is lacking for the major merger scenario. So this means that, very likely the northeast shelf is the second orbital wrap of the tidal debris from this event. So our preliminary comparisons favor scenarios in which the progenitor completely disrupts, or at least deposits the core within the inner 4 kpc of the disk. And from the metallicity distributions and also just the comparison between the various shells in the galaxy, we do have support independent of the models for a common origin scenario. All right, so I'd like to take an interlude here from talking about streams and shells and just briefly mention some ongoing work with the disk that I hope to have submitted by the end of this summer. So I've been mentioning the splash data across the disk, right? And we also have this exquisite photometry from the FAT survey. And there have been analyses of the disk that focus either on just metallicity information from the photometry or just kinematics from the splash data. But there actually hasn't yet been a joint analysis of these two things. So I've been working on that, doing a kinematical decomposition of the disk and then exploring the metallicity distribution functions. So these are MDFs for stars that are highly likely to belong to the halo or the disk along the line of sight. So again, this is a position and velocity based on position and velocity probability criterion. So you can see that you have more metal core stars in the halo, but we do see a significant population of metal-rich stars in the halo as well. If you're wondering about these blue regions, basically what I did to make sure that these metal-rich stars are actually there is that I assumed some extreme case of contamination by metal-rich disk stars that are interloping along the line of sight. So even in that scenario, we still see this population of metal-rich halo stars. So yeah, hopefully that will be out by the end of the summer, and we can learn more about the major axis halo population. So far, everything I can see is that it's fairly distinct from the halo along the minor axis chemically. Okay. So for the second part of my talk, I'll switch to discussing isolated dwarf galaxies in the local group. So this is an ongoing spectroscopic effort with the IMACS instrument on Magellan to try to characterize some of these systems. So what are some outstanding questions for dwarf galaxies in a hierarchical assembly scenario? Again, this is a very biased list of questions based on what I'm interested in. And here I'm showing an image of MGC 4449. So this is a dwarf galaxy in the local universe. That was one of the early clear pieces of evidence of these, dwarf-dwarf interactions where you have the stream of another dwarf galaxy associated with this starbursting dwarf here. Okay. So the first question is sort of what is the lower halo mass limit for dwarf galaxies? So this has to do with the galaxy, halo connection as well, and this relates also to ultrafaint. So Josh Simon has done a lot of work on that in particular. And there's also a related question is, sorry, I'm blanking. Anyway. Oh yeah, satellites of satellites problem. Sorry about that. So basically, we expect that structure formation should continue down to the lowest mass scales. And what are the expectations for, the luminosity functions of satellites of satellites? So the complement to the question of what is the mass function of destroyed dwarf galaxies is what is the expected surviving galaxy luminosity function. So there's been a lot of work on this recently in the local volume. For example, the Saga survey, looking at the population of satellite galaxies, and recently also the ELF survey, which is finding contrasting results. And this is also something that has to do with the interactions between the satellite population and the host galaxy as well. For example, you can have a lot of destruction occurring from interactions with the disk. And lastly, the question that I've been trying to partially address in the time that I've been here is what fraction of dwarf galaxies experience significant late time mergers. So again, we expect that most of the merging activity would occur early on in the evolution of dwarf galaxies, but there should be some sample for which this is not the case, and we should expect to find these galaxies, somewhere within the local group. And we do see evidence of tidal features around dwarf galaxies in the local volume, as shown in this example, but also from larger surveys. Okay. So I've been focusing on isolated dwarf galaxies because they're more likely to have experienced recent interaction with another dwarf galaxy compared to satellite galaxies. So we do have evidence of at least one satellite galaxy in the local group that seems to have experienced potentially a recent merger. This is Andromeda 2. A satellite of M31, but we don't have any clear evidence for the isolated dwarf galaxies yet. So this is from a theoretical study, that is assessing the expectations. Basically, the results are you should expect approximately 5 isolated dwarf galaxies to have experienced a significant interaction since redshift 1. So if you look at satellite galaxies within the real radius, you can see that many of them, you expect like 5% or so to have experienced a recent dwarf-dwarf interaction. This increases to much higher levels when you go beyond the VL radius and increases as a function of distance out to 1.4 megaparsecs. So with Magellan, we can look at a couple of these isolated dwarf galaxies that are a little bit closer to us, that are about at 500 kpc away. And particularly, I'm looking at 2 systems that have unusual stellar populations. These are NGC 6822 and Phoenix. So Phoenix exhibits bulk prolate rotation, which is unusual. It's the same as Andromeda 2, which is that satellite galaxy that's suspected of having experienced a merger. And NGC 6822, although it does not exhibit bulk prolate rotation, does have a prolate rotating inner core. So here I'm just showing the bulk rotation of Phoenix and then just a map of NGC 6822. It also has an H1 disk with a hole punched out, although this is probably due to some internal feedback mechanisms. And this is just an example of, some of the IMACS fields that I have placed or, we'll get more data on this summer, hopefully, in this galaxy. So it's not just the prolate rotation, but also the rotating part, you see spatial segregation in the stellar populations, where one population is more metal rich, or has younger stars compared to the other stellar component within these galaxies. So both of these galaxies are actually lacking kind of detailed chemical abundance information, particularly Phoenix. There have been some, and I'm talking about the red giant stars in particular, there have been some measurements in the core of NGC 6822, but the published measurements are limited to metallicities, and we don't have information along the disk and the spheroid as well, just to probe, broader formation scenarios for this galaxy. So just as a reminder regarding the importance of chemical abundances, so we can probe a galaxy formation history with these measurements. And this is a plot, although old, that I like to show that I think illustrates this concept well. So you have the alpha to iron ratio versus metallicity, and here we're looking at Milky Way galaxies and a number of classical dwarf galaxies, which are the colored points. So at high metallicities here, you can see that there's a clear difference in the alpha to iron ratio. In brief, the reason that this results is that calcium and magnesium empirically track yields from core collapse supernovae, whereas iron has contributions from both core collapse supernova and type 1a supernova. It also can be taken as a rough proxy for time, because in general, galaxies become more metal rich as they continue to evolve. So early on, the yields in terms of metal production are dominated by core collapse supernovae. But later on, as star formation activity becomes less efficient, you have more domination by type 1a supernova, and you see this decline in the alpha to iron ratio. So the difference in the alpha to iron ratios at fixed metallicity is a consequence of basically the different star formation efficiencies of these galaxies. So in this sense, if you see differences here, it can be taken as stellar populations with distinct evolutionary histories, and we hope that we can use that type of information to learn about isolated dwarf galaxies, and possibly discover things like merger remnants, although we don't see any clear photometric evidence for that right now. All right. So I've been measuring abundances from Magellan IMACS spectra using spectral synthesis. So this is an adaptation of a pipeline that I developed for my thesis work with DEIMOS applied to IMACS. So I've done this for both the 1200 line grading and the 600 line grading. So moderate resolutions, roughly 4,000 or so for the 600 line grading in this configuration, and 11,000 or so for the 1200. So what you're looking at here is the spectrum of a red giant branch star in NGC 6822, which are the black lines, and then the best fit synthetic spectrum here is the red, and I've highlighted regions of the spectrum that are sensitive to variations in magnesium, silicon, calcium, and iron. So we can leverage full spectrum synthesis to obtain bulk constraints for the alpha to iron ratio and the metallicity of the spectrum, although we're working with stars that are fairly distant for a 6.5 meter primary. And also, although we're working at lower resolutions as well. But the benefit of working at these lower resolutions is that we get higher signal to noise per pixel, so we can look at these faint stars at the tip of the red giant branch within these galaxies. So very quickly, I do have some very preliminary abundance results for NGC 6822, but don't focus on them too much because it's a work in progress. It's difficult to interpret them currently because the masks that I have for this are actually the spheroid and disk populations for which no prior data actually exists, so we don't know what the expectations are. But we do see potentially evidence maybe for like 2 different kinematic groups, which may be some evidence of rotation, and potentially 2 groups within the alpha to iron ratios as well. So, the hypothesis here is that NGC 6822 and Phoenix may have experienced kind of recent dwarf interaction, but even if that's not the case, abundances are still useful to learn about their histories. And if that were the case, it would still be interesting because that would mean the prolate rotation would have to be a result of some, internal processes within these galaxies. So again, hoping for some time in 2022b, so I can finish up these observations. All right, so I'd like to conclude my talk by a quick view into the future in terms of prospects for resolved stellar spectroscopy in the local universe. So ELTs will provide an extra 2 or 3 magnitudes of depth into the universe. So this will bring a plethora of galaxies into spectroscopic reach. So roughly 80% of these galaxies will be dwarfs, but there will also be some, Milky Way mass galaxies in there as well. And I guess I just answered this question. What does this mean for resolved stellar spectroscopy in the local volume? It means that we'll be able to do this type of work beyond, the current rift limit or so of 1 megaparsec. But before spectroscopy, we need photometry on which to design our observations, but also, photometry is useful in its own right, and you can learn a lot from it. So the Roman Space Telescope will provide resolved red giant branch imaging out to 10 megaparsecs. So something like the FAT survey, which was done with 432 pointings of the Hubble Space Telescope, you can now do with 1 to 2 pointings instead. Yeah.
That's the point you made between GSS and other components show similarity and detailed differences.
Yeah, so we don't have detailed abundances for all of the shells. We don't have them in the west shelf or the northeast shelf because the spectroscopy is too shallow and we'd have to resort to co-addition, which we haven't done yet. But in that 2021 paper I showed earlier, which I should have mentioned, I did do a comparison between the 2D chemical abundance ratio distribution, so the alpha iron ratio versus metallicity for the southeast shelf and GSS, and found that they were fully consistent, which we would expect if, they likely originate from the same event. This was looking at GSS fields also that were along the high surface brightness core. So the high surface brightness core is more metal rich, so you don't see this metallicity gradient so much within that region. Okay. Great. All right. So again, with Roman, you can just do something like the FAT survey, which has had a super high scientific impact with 1 to 2 pointings, and you can cover an entire system like the M81 group in a single pointing. So in terms of spectroscopy, we should be able to do resolved red giant branch spectroscopy at the tip of the red giant branch for the brightest tidal features out to about 3.5 megaparsecs into the local volume. So this is something that can be done with ELTs, particularly with the moderate resolution spectrographs. And, I like to say that Andromeda is a stepping stone to the local volume because we can really expect the data quality to be similar at the next observational frontier compared to what we're currently doing at the edge of the local group. And also the techniques that will be used are similar in terms of working with moderate resolution spectroscopy. And you'll also, we won't have the benefit of 60 phase space information as we do in the Milky Way. Everything will be done obviously in projection, as is the case in M31. So developing a good understanding of its merger history is, in my opinion, very important as we start to expand into the local volume. And the same is true for the isolated dwarf galaxies as well. All right. Well, I guess I finished a little bit early, but with that, I'll take any questions.
So there are globular clusters that are analyzed in one. I should say that then the mention of the globular clusters that are potential kinematically image that and delta and how do it.
Yeah, that's a really good question. One thing that's interesting about the globular cluster population is there aren't any that are superimposed on the sky on the main system of tidal features. Yeah, the ones for which there are chemical abundances for some of the globular clusters within the inner regions, the inner 30 kpc or so of M31. And I have done a comparison of those to our chemical abundances in the smooth component of the inner halo, and they seem fairly comparable as far as we can tell. But again, we're just looking at both alpha ion ratios and analyses. Yes.
Combining the two methods, the work we talked about here for the studying the sort of follow-ups on Andy's point that we consistent ways to test for that.
Mhm. You're talking about like a group infall scenario? Yeah, that's something that I've been interested in. Theoretically, there have been some recent explorations of group infall, but they've mostly been from dark matter only simulations. I think if this merger event was something like the third most massive member of the local group, we would have expected to have brought in satellites. In terms of the other fainter tidal streams that we see in M31, it's difficult to connect them directly to the GSS unless they have like similar chemical composition, which we wouldn't expect the satellites to probably have. You know, there has been a lot of work to try and characterize the satellite galaxy population, particularly in comparison to the Milky Way, mostly from Dan Wise's group at Berkeley. And I think that they're finding the possibility that, you know, many of them do have fairly similar star formation histories. I'm not sure what the right way to interpret that is, but it's possible that some of them could have brought them together at a similar time. I'm not sure, but that's a good point. Yeah, that's another thing is we're basically completely lacking proper motions aside from both proper motions for like M31 as a whole. So there has been, you know, some effort to try to get proper motions for certain structures, but it's just a huge investment in terms of HST time. And Gaia, at least, yeah, previous Gaia has not gone faint enough. I don't know about like DR3, but I assume it will probably be similar. Yeah.
Question for Josh on that. Constraining what the mass and velocity of the GSS progenitor magnitudes measure. How would it help comparison with
Yeah, prior to its merger. So in order to do that, I think, yeah, you would have to, at the very least, the progenitor material would compose of the giant stellar stream in the system of shells. So I guess you could add up the inferred mass and luminosity from that, but I don't know that anyone has actually attempted this. It's an interesting point. Yeah, and something that probably would be aided by the use of models. Yeah.
Expect to see that have distinct substructures in both places.
Yeah, that's a good point. Not as obviously within our own local group. So there has been, for example, from like a Subaru HSC, you know, wide survey of the local universe, you see like clear tidal features around like order 3% or so of dwarf galaxies. You know, there were some papers claiming to see evidence for a stream-like feature for Andromeda 2, but I don't know if I personally find that conclusion to be robust. So for now, to my knowledge, there's no like glaring stream evidence of these types of events in our local group.
What can we look forward to with long observation? How will that complement the current future spectroscopic surveys?
Yeah, so for Roman surveys of M31, previously I would have said mapping the southern component of the disk, but that's actually already being done with HST and is almost complete. I'm not sure if it would be better for targeting the innermost regions of the galaxy, including the bulge, which we don't know much about, and well, it's very crowded, but that's one potential area. One region in M31 that we don't know very much about is the outer halo. That has been difficult because of the dwarf, like the contamination from the Milky Way foreground. And also, again, just the huge area of the sky that you need to cover. So if you can just do, you know, a small set of pointings and cover that entirely, I think that would be an area for significant gains. And just going also just much deeper in a lot of these systems in terms of the star formation histories. We don't have global star formation histories for basically any of these tidal features. It's like all pencil beam HST based pointings. So yeah, those are, I guess, a few potential areas off the top of my head. For Roman? Yeah, I am not currently sure, but I hope so, because it seems like a pretty obvious thing to do. But yeah, that's something I'll have to check. Mhm. Yeah, that's a really good point. I haven't seen that much work making detailed theoretical predictions for it. To the extent of my knowledge, it's mostly, you know, the Beeson et al. Paper, and that's looking just at like a single galaxy formation simulation. I think there's more work to be done in terms of like investigating this and multiple like different Milky Way mass simulations or full local group environments, like the Elvis simulations, Fat Elvis in particular, for example. Yeah, and you could assess, you know, if there's some sort of distance range in which you don't need to, I guess, worry about whether something has been going in and out of the VL radius or something along those lines as well. For NGC 6822 and Phoenix, they are close enough that, especially for maybe Phoenix, you know, it's possible that it may not have always been outside of the real radius, but I don't know that that's something that we can currently assess with proper motion for those galaxies. I'm not sure. All right, thanks everyone.